is 2026 by the way. Mwaka gwanchukachuka banji bagira omutabulomesite bagiraba kale munauganda kuma si ekwasinga okulungi ensi. So this from Uganda, have hope and look forward to better times that are coming. Right, enjoy this.
Welcome then, everybody in the audience, this very fine interview. We have a crew from the Animal 266 TV that also is found on Telegram and on YouTube. We shall have various assistants to assist in reading out the review questions that were solicited from the community and audience that receives this lecture. Please listen closely, for we shall have the questions or matters first of all raised in the native languages in which they were first presented, but also we shall have an interpreter give us a version in English where necessary, so that everybody can follow. For those of you that have the interview or review paper, of course it shall help that you follow along, looking at the notes, especially looking at some of the mathematics presented alongside the responses given by future Professor Joseph in response to most of these matters that were raised. So that's it. Listen, enjoy, sit back and relax, and get ready to take the journey into the most interesting modern theory, practice, and explorations in mathematics, computing, and very many other fields as attached by Transformatics and its applications across various sciences, arts, and humanities. Welcome and please enjoy an interview and meta-review of Transformatics Introductory lecture of 3rd February 2026. A video mini lecture on the new mathematical theory of transformatics as applied to basic sequence analysis was delivered on 3rd February 2026 by inventor of the theory and also principal investigator on the Transforming Executable Alphabet TEA Computer Programming Language project, currently one of the best examples of how transformatics can be applied in practice. The lecture was the first to be delivered explicitly for the purpose of introducing transformatics to new audiences, and it happens to have come at a time when the most critically important work on formalizing transformatics, the Transformatics 101 mini-thesis, a review and distillation of all earlier work underlying transformatics, is undergoing further revision and is also being integrated into an upcoming book on applying transformatics in genetics, slated for 2026. However, not everyone coming to transformatics has fair footing in the associated background theory and ideas, and thus this necessary paper that is actually in the form of an interview in which Joseph responds to 8 important problems raised by members in the audience concerning that introductory lecture, especially touching on the notation used in transformatics, the important matter of different kinds of symbol sets, the Anagram Distance Measure, ADM, introduced in the lecture, and what lies ahead beyond just the ADM for interested students and researchers. The material has been presented almost verbatim, some questions being presented in the native languages, Ganda or Luganda and Cwezi or Runyakitara, as they first came to us, all based on the points solicited from community members since the lecture first went online. And the answers are then augmented with sufficient references to existing transformatics literature to help galvanize the discussion and make this paper serve as an authoritative future reference tool. If you have a copy of this paper concerning the interview and meta review, you shall find that the key words are review, interview, mathematics, foundations, transformatics, sequence analysis, notation, symbol sets, and anagram distance measure.
Welcome then, everybody in the audience, to this very fine interview. We have a crew from the animal.
Alright then, let's first have some greetings from some of the active netizens and members of the internet community that are with us through this interview, and then we shall kickstart the interview after the greetings.
Yes, mwala nnyo okutuyita okujja okubegattako mu ngeri y'akaboozi okuyiga n'okuba nga tutambulira wamu nga abakerufu okuva wali Cwezi research abakulembeddwamu principal investigator Professor, my future Professor Joseph Wilrich Utalo, era nga bagenda kuba nga batuyitiramu engeri y'okunnyonnyola n'okunyikiza amagezi amapya agaleeteddwa mu ngeri z'okubala okuyitibwa Transformatics, era nga ffe tuli basanyufu nnyo okubegattako wankubadde oluusi ekituukirako nga biyita mu mikutu gino egy'oku intaneti mitimbagano egyo oluusi nga n'empapula ezo kale tuzifuna n'engeri y'okuba nti okwagala zeetegereza obulungi ne tulabika nti tuzikubisaamu era nga ffe tubeera nazo tuzikuuma era amagezi ago tugeyagalyamu nnyo kuba gaffe nzaalwa za wano Uganda. So okujja okubeera mu talk show eno, okubeera mu interview, kubanga mwamala dde otumanyiiza ate nga muliisa obwongo emyoyo gyaffe, kale n'okuba nti tusanyuka kubanga tuwulira amagezi oluusi nga tugako mu nnimi ezaffe eza wano. Mwebale nnyo Cwezi Media Lab, ate naddala mwe bakwano baffe aba UIC Uganda Internet Community wali Telegram. So yes, tumaze okulya ekyemisana era nga tumaze okuwagala bulungi obwongo tuwulirize buli konna kemugenda otunyonnyola, naffe tubeeko kyetuyiga ate tulabe gye tweyambisa amagezi ago ge mumaze okusengeka obulungi.
Tugebawo bwenyumenda nyoba IC kale linguko okutuleetera amagezi ago gatwikyaho kikolwa kirungi muno kandi muno bani Cwezi research mali kama kabaha kandi naimwe
kata tuleka kizima obundi tubata takumanya kufa mu nsi muno tuli mu kasunkani kaza tekinologiya yingi zitwetoloire zikukira takyasobola nokusobola tugenda kubirisa oba kutuleetera za shows ezo mulingo gw'okwengesa n'abaana bato ondi bamazire nga isomero ondi bamazire emirimu yaabwe naabo kujja koire baikala hansi baikaza awo twena tuteirewo hali mulingo gwa za bluetooth ezo kale tuwuliriza kwetegereza kulungiza science mulesere ebitabo bundi bitwikawo aitu ennimi zindi batakuzikenga ati kura ntigenda kuba ntusobora Runyakitara bali mukama yakubaire n'abaha ensozi ez'obusinge okusemererwa kandi kuranti maraka ganyu mirimu yanyu kuyongera maiso simubona ebi nokuba tensiona nimwegesa kulembera kandi mulema kuba ninywe bakama bazimu za transformatics ezo mathematics twakumanyire nambereho ziyitirana baitu kali tugenda kuba ntuwuliriza talk shows ezo mulesere interview ubundi kali naitwe tulina ebikaguzo twahereise tunihire mujja kuba nimutugarukamo kuba ubundi physics ezo mayanga transformatics ubundi zigumire ti mulingawo kali kufuurafuura za sequence ezo baitubundi mulingo gwa methods ubundi ezimu zasobere mulingawo kwesa za calculator ati mulingo gwa majaji kale bagesere ti transforming executable yes tube nago tungera ku geyamisa kulungi ngebale muno professor abamakerera kunanywe kensibaitu kandi na university ya Bunyoro kuba nitwegesa bundi kubarogo kwakwenje kukaleta language za miti nitwegesa omulingo gw'okuhandika enamba ezo na symbol sets kale tugenda kuba nitubuuliza kurungi baana bato tulere se nga kuli waira kufoora abara tusobola byona.
Welcome everybody in the audience to this very fine interview.
Welcome everybody in the audience to this very fine interview.
The first question concerns angled brackets for sequences and whether there is any relationship with loon numbers.
Mwaka kuhoirogwo 25 haliho films za academics za trukire most likely kurugaha NML chano ya Professor Waitu kama Joseph Weira bakabaza ha low numbers ezo na low number system yagisobora milingo yokwegesa ebimanyirwe abyoma binu ebya Linux kukenga ebisani gamba nke birumwente oba abantu nibyeyambisa kubara kwina enamba ibiri zonka signal na anti-signal. Is it that brackets obulwaho bunu bwa low numbers obya twanjulire nibwo bumu obuli mu Transformatics. I did see an interesting video on YouTube concerning the July 2025 paper on low numbers and the low number system. I think it was published via preprints by future Prof. Joseph, that was telling us things about using these bracket symbols, signal and anti-signal, to automate machine learning tasks such as the counting of cows, goats, or people in a crowd using photos and computer vision on Linux. Is this related with this Transformatics stuff?
Yeah, so sure. In Transformatics, the convention since around the arrival of Transformatics one-on-one mini-thesis of October 2025 has been to express sequences using the angled brackets, the opening and closing angled bracket as delimiters, and not, for example, the typical curly brackets as are used in sets. No, the square brackets, that are common in lists for some computer programming languages, and which are also used for ranges in calculus. But no, the use of the opening and closing angled bracket in Transformatics has nothing to do with the theory of low numbers, which define the opening bracket as signal and the closing bracket as anti-signal. Something like 1 and 0 for arbitrary information expressed in binary form. Even though, both theories have been discovered and developed by the same person, aka a future Professor Joseph Willrich of Cwezi. So, however, it still does make sense, especially when, parsing complex sequences, or rather higher order sequences, such as, a sequence of English words expressing an essay as a collection of paragraphs. The main sequence would start with, signal, and after that, the next occurrence of signal would help indicate further levels of nesting or individuation, paragraphs, sentences, and then individual words, inside which a word sequence then merely has, commas between terms, such as its letters. And then it closes with a single angled bracket, the closing angled bracket, which is the anti-signal. So then the essay as a sequence, of words, sentences, and paragraphs can be analyzed at the most abstract level using just signal and anti-signal. So that without even bothering, to look at or count the letters, and without even concerns about the language the essay is written in, one can just analyze the sequence for how many paragraphs, sentences, or words it contains, merely by processing those two low number symbols. Also, whether or not some paragraphs are merely sentences, or whether, some sentences contain just one word, can be determined even with all the letters and punctuation having been eliminated from the essay, as long as these structure defining symbols have been well preserved or well applied. So we could apply the low number system analysis method in special kinds of sequence analysis, analyzing sequence notation expressions, such as, in parsers or when applying parsers, to be precise, But no, Transformatics doesn't necessarily use them because of their low number system meaning or relevance.
Welcome again, everybody, always. This very fine interview.
Question 2 concerns how inverted pi became a length quantifier.
My background is in engineering sciences mostly, and symbols in mathematical formulas, and especially in physics, do mean a lot for me. Such as when the extended ace is used to mean integration in Newtonian mechanics, or when we use sigma symbol to mean summation in Riemann sounds. So what is the logic or history behind this use of the inverted pi? Because it seems as though I don't follow quite well, and yet it's possibly nothing to do with a constant 3.14.
First of all, the idea of cardinality used in transformatics relates to that of the length of an expression, which for most cases in transformatics, definitely means the length of a sequence, or rather how many elements or members a sequence contains. So this idea is one of the first fundamental concepts that was developed by the inventor of this theory, since it goes back to the first mathematics papers that I wrote as early as 2020. So when formalizing and laying down my ideas on the general cardinality of numbers, as well as placing finite bounds on the size of expressions that might result from the addition, subtraction, but also division and multiplication of two or more numbers. So GTNC, the general theory of number cardinality, first presented the notion of a sequence's cardinality as used in transformatics. However, later these ideas had been extended to quantifying and analyzing expressions that are in numbers, such as sequences of English words, strings in computer programs, etc. So it was decided to abandon the original symbols, which were just a C sometimes, or C with a subscript of the expression, the nature of the expression, like a pure number or fractional or the variable symbol, etc. So symbols, and then instead use a more unique symbol. So I decided that it was better that we use something a bit more prominent and rarely found. And so the inverted pi was one of those ideas that struck very clearly as a great candidate for this. So this symbol got chosen. Also, perhaps first formally defined in the Anagram Distance paper, and especially because of its distinctiveness and how relevant this measure was in formalizing many of the other ideas already being developed at that time in transformatics. But no, it has nothing to do with the use of a pi symbol, the popular pi symbol in geometry and much of mathematics, also in some areas of physics. And no, it's not related to the mathematical constant used to express the ratio, of a circle's circumference to its diameter. But perhaps its relevance, I think we could relate that to the fact that, at the time when it was being formalized in transformatics, indeed, as the inventor of that theory, being the principal investigator, so-called pi, at Cwezi Research, and yes, I still are, and my decision on what notation to use for the critical parts of the theory heavily still are mine to make as the sole benevolent dictator, of all of transformatics theory until, maybe someone else picks it up.
This very fine interview.
Question 3 concerns stars versus rap, and whether transformatics can help us identify palindromes.
Omanyi Professor Lutalo Olusi asabsesa wawagamba nti stars emunyenye ziyinza okuva mu rods emmese magezi gaki gano gayogerako zino ngeri za kufuula zigamba nga transformatics zetwawulira lumtauto oba waliwo engeri kale ez'okubala endala zetutanategeera naddala ebintu ebyenjawulo naye nga oluusi bifuukafuuka ate ne bitandika n'okufaanagana.
So first of all, note that many people are new to such mathematics as transformatics shall without doubt get lost and only see stars if we had written, most or all of the mathematics using, say, traditionally palatable Greek letters, or perhaps, some of the recently well introduced alternative modern, African hieroglyphs and the various alphabets associated, such as, Ozin, or perhaps the crypt of Medina that were first formalized in the book Grimoire Lumtauto. I think this was late 2025, around October there. So, and yes, even though books like Lumtauto that without doubt help, bring the mathematics of transformatics to the arts and humanities, likewise contain many, mentions of peculiar magical things, such as forming words using literal mirror operations, so as to invert or reverse spells laterally, or perhaps to work against any such reversible magics, Yes, like when you don't want spells that can be reversed, or you want to, to reverse spells by inverting, or known black magic hexes and such. So, perhaps, and I'd say somewhat reminiscent of computer science concepts such as, palindromes and palindromic expressions, of which, yes, the choice of this example, that we have, star, as a word that also reads as rats, if you invert it. It might be a bad choice when we have to, look or think of palindromes. And otherwise we could have instead thought of words like ewe, E-W-E, or I-E-Y-E, which read the same, from the right as from the left. So even if you invert it using mirror transforms, it would still remain the same. But no, this wasn't about palindromes, even though it somehow might be related. So the idea being communicated here actually is about, discovering interesting things, about certain expressions when we look and relook at them, under the transformatic sequence analysis microscopes. For example, you find that two or more words, share the same root, something that in transformatics we might relate to the linear algebra concept of a basis, like when you have multiple or different matrices or vectors, and you're trying to find their orthogonal basis, or that unit vector or unit matrix from which they can be reproduced. So that concept there, you see, and we see that being demonstrated in this lecture with our two different sequence expressions, STARS and then RATSS, because when you read them, like if you were to read it quickly, as just a phrase, it might read as star S and then rat SS, but despite being funny, and perhaps it wasn't meant as a joke, but it could be, one, especially relating to star SS, and rat SS, stars and rat SS schools that only focus, on arts and making their students, artist stars, the guys that focus on only MDDs and the likes, the Namasagalis of those days. So these examples are in fact a great example of how we can reduce expressions to only their unique set of elements, what we might refer to as symbol sets in transformatics. And yes, we find that these two expressions both map to the same exact 4-letter set, A-R-S-T. After you reduce star S, and after you reduce rat SS, you end up with that symbol set or that sequence of just 4 letters. So even if both sequences are 5-letter expressions and that they are spelled differently and even mean different things, and yet they reduce to the same symbol set. So transformatics is great at exploring many such problems, involving treating of things as sequences and not just words or numbers as might be treated of, for example, in linguistics or in ordinary mathematics respectively. So hopefully this clears up the confusion and yes, does away with those ratty jokes. Yeah.
Once again, everybody always this very fine interview.
Question 4 is about whether there are 2 types of symbol sets or 1.
Zino endimi za symbol seti zikuzuka nizibuzabuza ubundi tukura naturali ubundi specifica kandi ubundi unspecifica. Hati mukisoboye ibika bya symbol set zino bingaha kandi bikumanyisa ki?
These symbol set concepts sometimes become confusing because we sometimes hear of natural symbol sets, then also specific and sometimes unspecific symbol sets. So how many kinds of symbol set families exist? And are they 2, 1 or more? Interesting and quite important that readers and especially students of transformatics learn to distinguish between these different concepts of symbol sets. First of all, concerning what is meant by symbol set, note that for any expression, or rather a sequence expression, whether a number or an arbitrary collection of symbols such as letters that form a message in English, or perhaps the sequence of symbols that define a T computer program. When we reduce any such expression to its unique distinct elements, then we have what in transformatics is known as a symbol set. That's basically it. The term set in symbol set is important here because unlike the sequences that most of transformatics is about, a set cannot contain the same element more than once. But also, and important with regards to transformatics, which especially focuses on the study and analysis of ordered sets. Once we need to care about the elements in the set, or rather, the thing we need to care about most is actually that the elements in the set are in some order, or that they conform to some order. So, such as which symbol should appear before the others, and that when we start considering more advanced concepts, then we want to look at something more advanced than sets, and so sequences come to mind. So for the case of symbol sets, which are still sequences, but yes, they are sets in the sense that, for example, symbol sets don't allow duplication. Yes, but order is important. So order indeed does come in handy when we wish to preserve some information about whether the element in a symbol set originated from
a sequence where it came first or was followed by another or something like that. So we want to make sure we preserve that in a symbol set. So in this lecture, we are shown two sequences, and we see that if we reduce the first one to only its unique elements while preserving the order of the first occurrence in either sequence, then we end up with star ace becoming just star. So the symbol set corresponding to star ace will just be star, because the ace has already been seen, and so we don't want to repeat that. While for rat aces, it definitely becomes rats. So in either case, we eliminate repeated terms, but otherwise we preserve the order in which the symbols occurred in their original expression. So these kinds of symbol sets are technically called implicit symbol sets. Implicit symbol sets because the only thing here that matters is that we want to know what the unique symbols in the sequence are. But otherwise, we would have what is called unspecific symbol set, when the only focus is on the ordering of elements by their order of first occurrence in the original sequence, and by no other criteria other than avoiding repetition or otherwise. So if we care about just which symbols are in the original sequence, the unique symbols, it's an implicit symbol set. And if what we care about most in addition to that is the order in which they first occurred, then we're talking about the unspecific symbol set. So we usually write such symbol sets as shown in the first two cases using just the Greek letter psi, and the letter psi looks like as a V with a dash through its its center there, followed by the symbol of the sequence being analyzed with round brackets. So you have psi, and then you put the variable name or variable symbol in brackets after it to indicate that this is, for example, the implicit symbol set. And otherwise, we decorate psi with a heart accent if we want to talk about the unspecific symbol set. So these notations are important because mathematics uses a lot of sometimes figurative language or symbolism, but this symbolism and the symbols used are non-ambiguous. If you look at one symbol and in another instance they use a different one, the things meant normally are different, so you have to know exactly what is being talked about. So concerning these two types, it is worth noting that many times in transformatics we might just write the notation for the implicit symbol set when we actually imply or mean the unspecific symbol set. So sometimes, just to simplify, or when all that matters is the unique elements in a symbol set, then we might do away with the heart, and still we have a symbol set, but we are explicitly talking about the implicit symbol set. So this especially because either kinds of symbol sets only focus on the sequence being analyzed, and also that the unspecific symbol set is just another version of the implicit symbol set that a given sequence might have. So the other important type is that of the natural symbol set. In this type of symbol set, which we write in a similar way but with a psi symbol bearing a subscript, such as shown in the bottom left expression on the blackboard. For example, as psi AZ, we process the symbol set relative to some base, beta, or some reference alphabet, such as AZ in this case. So AZ, for example, is the Latin alphabet. So, for example, in this lecture, we process the two sequences relative to the Latin alphabet, and that's why we see psi AZ. And so that, as with all natural symbol sets, the resulting sequence are such that the terms are ordered in a way so that the terms in the resultant sequence preserve their natural order, of first occurrence in the corresponding bases ordered symbol set. So the base matters here, not just the sequence we're trying to analyze, but also the base. So if the letter E comes before the letter F in that alphabet, and you have a sequence that contains that, you want to preserve that order. So thus, even though both example expressions, had different orderings of the 4 letters, R, A, T, S, and yet when transformed into their natural symbol set under base AZ, or perhaps more mathematically correct under base 36, because base 36 already contains all the 10 digits in their natural ascending order, and it is suffixed by all the 26 letters of the Latin alphabet in their natural order. So we could do away with base AZ and deal with base 36. So we see that we correctly see that A, the sequence then reduced to the same natural symbol set, having the ordered terms A, R, S, T. There were no numbers, so we are only dealing with the elements in the Latin alphabet here, even when we are dealing with base 36, and nothing else when processed under the same base. So we see that if we started out with a sequence that had star S and transformed it into rat SS, still the two symbol sets, before and after the transformation would still be equivalent. Then also note that since the OC is the orthogonal symbol set identity paper, we also sometimes refer to natural symbol set as the base symbol set. So some of this terminology has been laid down or has been formalized as more research was happening on this theory. And then perhaps also less commonly found in our transformatics literature thus far, what are called specific symbol sets. So these were also first formalized in our orthogonal symbol set identity paper of April 2025. And these, though somewhat related to the base symbol set or the natural symbol set, in the sense that they are computed with some specific base in mind, and that we differentiate them from the natural symbol set by adding a heart accent to the psi base symbol set. So implicit has just the psi, and then the symbol of the sequence. But for this case, we add that heart accent, and so we see that they are different from all other kinds of symbol sets we have discussed thus far. First of all, because apart from ordering the terms in the resultant sequence based on the natural order of first occurrence in the reference base alphabet, they also enforce a filter on the sequence expression that results from processing or computing this symbol set, and it has to only contain the symbols in the base that is being referenced, and nothing else. So what this means, for example, is that if we had an expression such as star S1 O1, to, for example, mean the best student in a school senior 1 class, stream O1, some schools name their streams maybe after east, west, blue, red, blah blah, but assuming the stream name was O1. So then when reduced to its unspecific or implicit symbol set, that is just psi with a heart and then in bracket the theta symbol or the symbol of the sequence, it would result in the sequence STAR10. So for example, that would be what we have, because that's the natural order in which those symbols first appear. While in its natural symbol set, under base 36, would be 0, 1, A, R, S, T. So notice here that there would be some changes between these. And yet if we compute the specific symbol set under base 2, which only recognizes only 2 symbols, 1 and 0, the resulting set for that expression under base 2 would just be the sequence 0, 1. So that's important to note. And also don't forget that when we have a specific symbol set, and then we have a natural symbol set. The natural symbol set relative to a base, for example, in this case, in base 2, 0 comes before 1. So even if in our expression we had a 1 coming after 0, or 0 coming after 1, we have to enforce the order in the base. So important to note is that in case we had to compute a natural symbol set of that expression under a restrictive base, such as base 2, and yet the sequence being analyzed had symbols not belonging to that base, then a plausible solution might be to still process the symbols in the referenced base by their natural order in the base. And then for those symbols that are not in that base, perhaps we'd process them by first occurrence, order of first occurrence in the expression. This, however, might be a corner case because we have not really formalized this before this, but it is derivable from what we already know. And though we can't call it a natural symbol set, perhaps we might call it the extended natural symbol set, or perhaps the natural unspecific, or the pretty natural. It's really not natural in the sense that as we've looked at before, so we could call it pretty natural. Yeah, nothing about superhumans or ghosts and such, but yes. Yeah, so as to emphasize the fact that it is not really like the normal natural symbol set we've looked at. So also, as for cases where we have to compute a specific symbol set, yet the sequence being processed contains no elements in the specified base, then the result would merely be the empty sequence or the empty set, because the filter that it enforces would kick out everything. And then maybe last but not least, especially because we mentioned the orthogonal symbol set identity paper that also helped clear much of the earlier confusion about symbol sets in transformatics, it would be good or useful to note that special kind of symbol sets exist that we might call the orthogonal symbol sets. And these are merely a kind of implicit symbol set that exactly reduces a sequence or expression to some anagram of a particular base's symbol set. So we have looked at the natural symbol set that could, for example, reduce a sequence to only its elements in a given base, maybe base 36 or base 10 or base 2. So in this case, if it's orthogonal, we would be reducing that sequence to a symbol set that actually is made up of all and only those elements that make up the basis symbol set. So that's all. These orthogonal symbol sets might be in any order. Yes, the terms don't have to necessarily be in their order of first occurrence, just like as we saw with the implicit symbol sets. But they must consist of all the elements that make up the alphabet of some base. That is important. So, for example, we have the strange and interesting expression, that I discovered while studying calculator interfaces sometime in 2025, and this number expression, we gave it a name, the hi-fi OC, the hi-fi orthogonal symbol set identity. Yes, so it consists of all the 10 digits from base 10, of course, that is one of the conditions, and their order is actually not the same as the base 10 symbol set would be. For example, they are in the order 8, then 6, 4, 9, 1, 3, 7, 5, 2, 0. They are 10 digits, but their order is not 1, 2, 3, 4, 5, etc. It's the way I've given it to you. 8, 6, 4, 9, 1, 3, 7, 5, 2, 0. And to remember this number, because sometimes it's useful to be able to memorize such constants, because it's a constant, it's a whole number, it's a pure number. Yes, you can memorize it using the mnemonic hi-fi dim get. Yes, so if you know why those things are useful, Masons, for example, have been using these memory tricks for centuries, and so this idea could come in handy for some mathematics students. So the very interesting thing about orthogonal symbol sets, just as with the orthogonal symbol set identities upon which they are based, is that if you shuffle their elements in any order, even the resulting sequence still remains an orthogonal symbol set relative to the base that gave us that orthogonal symbol set to start with. So it's because it's just an anagram of the symbol set of some base. However, of all the possible orthogonal symbol sets of a base, such as base 10, base 36, or the Latin alphabet, or for the case of biologists, the DNA alphabet, which has the nucleotide symbols, A, C, T, and G. There shall only exist only one symbol set that we can call orthogonal and also natural, meaning that it conforms to the ordering of terms as they are in the symbol set of the base, but yet also that's the ordering of the terms in the sequence. So that's about it. So to wrap it up, notice that we have talked about natural or base symbol sets, and we have also talked about the implicit symbol sets, and we have talked about the unspecific symbol sets, and we have talked about specific symbol sets, and then we have come up with a new term, or encountered what we may refer to as the unnatural or pretty natural symbol sets, and also then come up with this idea of the orthogonal symbol sets. So those last two, of course, have been introduced or merely developed as a reflection during this interview. So that's a total of about 6 different kinds of symbol sets, and hopefully all the confusion about symbol sets is reduced to nothing by now. However, and as you might have realized through as you might find out for yourself as you study and in practice, these may not be the only symbol sets, but the most important ones are most likely about just 3, especially the implicit, the natural, and then the specific symbol sets. But in reality, and also as you go about exploring in literature, you might find that there are many other kinds of symbol sets, and that we might define and develop many other types in the future. However, the ones we've mentioned are most likely the most important ones as of now, and based on what we currently know. So hopefully your answer or issue is well settled.
Question 5. Concerning the arrow symbolism, very common in almost all of transformatics literature and formulation.
So is the use of arrows in transformatics similar to use of arrows in calculus? And does it have anything to do with the limits or not? And what of their relation to the arrow of implication? Yeah, so that's wonderful, and it's a beautiful question, and it's great that it was asked by a student of mathematics. So for starters, note that transformatics especially employs arrows in 2 major contexts. First, when introducing the signature of a sequence transformer, and secondly, when applying a transformer, such as in expressing a sequence transformation. So sequence transformers are at the core of this proposed new branch of mathematics, and as you shall come to appreciate in the chapter dedicated to discussing and explaining how transformatics as a field of mathematics relates to other existing and earlier fields, such as statistics, set theory, logic, linear algebra, calculus, and others. A work which I would rather not divulge prematurely, until when you get to read or see it in my upcoming book on applying transformatics in genetics. You'll indeed appreciate that sequence transformers are in fact a furthering of several earlier mathematical ideas and notations, such as mappings that are very common in fields like linear algebra and calculus, for example. So however, in transformatics, the arrow used in the signature of a transformer is meant to especially do away with problems earlier notation, such as use of the equal sign in formalism such as bad meetings, transformation logic, would create. So that particular case of problems, for example, are among older mathematical formalisms that I discussed and critiqued as part of my review of the Oxford professor, Jeremy Gibbons' 1991 thesis on tree algebras. So in particular, given that sometimes a transformation results in a change that cannot be reversed, which can't directly return from the result to the original sequence, we then would want to avoid problematic notation, such as the use of an equal sign to depict, for example, a general or arbitrary chemical reaction or chemical transformation in chemistry. But also notations such as, scenarios where a colon is used in mappings for cases, such as in some algebras, and also where others might use, an equation to imply an otherwise one-way transform, such as in the case of bad meetings, formalisms we've talked about. We would rather write our mathematics differently, even though we might sometimes be meaning or appealing to similar concepts. So arrows in transformatics indicate the direction of a transformation. That is important, and this means that there would be no problem with using, an arrow that points both to the left and the right in transformatics. Such might be the case when we're dealing with interesting transformer such as Lomtauto. Lomtauto was formally introduced in the occult mathematics book Novus Modernus Grimaud Lomtauto. I wrote this under the pseudonym or alter most ancient priest Saimaz Magina. This was late 2025. So that transformer can help us demonstrate the rare case in transformatics where we might have allowed a transformer arrow to be replaced with an equal sign. This because the sequences that are transformed via this Lomtauto transformer can later be sent back into it without modification, and then they would produce the original sequence that gave us the input that we passed in. For example, if we took the word like language and under Lomtauto it becomes Lomtauto, and then applying that same exact transformer to Lomtauto would give us back the word language once again. So in such cases, we can also think of the transformer arrow as an arrow of double implication. Yes. So, however, that's about it. Transformatics arrows aren't a notation. That is like how arrows in calculus with formalisms, such as indicating the tendency of some variable approaching some constant, as we see used when expressing limits. In our case, the arrow is not one of tendency, it is actually an arrow of actuality. The arrow means that the value on the left eventually, or in fact, must become the value on the right, and vice versa, if it either is double implying or if it was right-left pointing. So typically though, for transformers, we write transformer function name and function signature at the top of the arrow, which typically points from left to right, and then place the source sequence to the left of that, and then the resultant sequence to the right of that. And also many times shall extend such an expression with one or more logical expressions, especially using basic mathematical logic or set theory notations that help rigorously specify the conditions or constraints on both the source and resultant sequence given their signatures, types, and the nature of the transform. So these other specification expressions might typically be placed immediately after or conventionally below the opening transformer signature expression, like after a single semicolon. So in sequence transformation expressions, we might either place the transformer name above the arrow or entirely omit it, such as we see shown in the examples on the blackboard in this lecture. Yeah, so I think that's it.
Question 6 concerning the limits on the anagram distance measure.
ADM is a real positive number. But does it really mean it can grow indefinitely towards infinity, even for finite sequences, or might there be a finite upper limit for ADM?
That's perhaps a function of the cardinalities of the two secrecies involved.
So yeah, thank you for being with us through the first half of this interview. Please note that we should be back after the break with the remaining second half.